Hello and welcome to this last lecture of our coverage of the basic principles underlying the equations of transport phenomena. And in this lecture, we shall round off our derivation of the governing equations by treating the energy conservation equation as well as the mass conservation equation. And along the way, we shall also have some things to comment on about the physical meaning of pressure in incompressible equations, as well as some discussion on the nature of energy dissipation as heat, the heat dissipation of energy. All right, so let's begin with let's begin with the energy conservation equation. So by now, based on the derivations we've already done for mass conservation and momentum balance, you will be familiar with the basic steps that we are going to follow. So the first step is to write out the conservation principle for a material volume, which is simply the rate of change of total internal and kinetic energy of a material volume must be balanced by the work done by body and surface forces plus the flux of heat through the surface. So the first term is essentially, we already know the we already know the expressions for body and surface forces. By taking the dot product of those forces with the velocity, we will naturally obtain the work done. So this term is not a problem to write down. The fluxes of heat through the surface, by this we mean non-continuum effects associated with the diffusion, let's say, of molecules that are able to transport heat from one region of the fluid to the other. So for example, you can think of once again the ideal gas, and if we have a gradient of temperature in an ideal gas, then molecules in the high temperature regions will have higher molecular velocities than those in low temperature regions, and random molecular motions that cause an exchange of molecules between these regions will tend to uniformize the temperature gradient. So this is the idea behind the essentially conduction of heat or the diffusion of heat. So we will introduce that as we go along. All right, so let's begin now by translating this principle that we've written in words into equations as we normally do. So the rate of change inside a moving control volume is capital D dt integrated over the moving control volume. So now the internal energy per unit volume we are going to represent by E. So this is the specific internal energy representing all the energy of molecular motions, internal bonds, etc. And then we have the energy due to macroscopic continuum level motion, which is simply the kinetic energy. So that's rho V dot V by 2. This V dot V is nothing but, of course, V squared. Yes, so this is the kinetic energy and this is the internal energy. And this must be balanced by now the work done by surface and body forces. So let's write down the body force term first. So it's the integral over the volume. The body force, of course, is rho g, and you have to take the dot product of that with V. Similarly, to get the work done by surface forces, we integrate over the area. We know that the surface forces are represented by N dot, the stress tensor, and this must of course be dotted by V to get the work done by surface forces. This is integrated over the area of the material volume. And now finally we have the net input of heat. So I should write here the input due to flux of heat to the surface. And this can be represented by a negative sign over the surface times the heat flux vector dotted with the unit normal. Okay, so this term deserves some additional explanation. Yes, so the idea here is that you imagine that you have the moving control volume resting inside the fluid. Now at every point we say that we can define a flux vector. So at any given point we can define a flux vector q, which tells us that, which gives us the local direction and magnitude of heat flux at that point. So now by looking at all the points along the surface, at every point we would have a different flux vector q, which could have any orientation relative to the surface. Now it's only at those points where the flux vector has a component along the normal where we'd expect this heat flux to lead to input or output of thermal energy, right? So if the flux vector is tangential to the surface, that flux of heat is not going to change the energy balance. It's only if it has some component along the normal. If it's directed along the normal such that q vector dot n is positive, then this will lead to an output of energy, hence the negative sign. Whereas if q dot n is negative, it means that q is directed into the body, and the added negative sign here would lead to a positive contribution to the total energy. So this is strictly the flux of heat, thermal energy, and mechanical energy cannot be transported in this way. That can only be done due to the work done by the forces as we have written here. Alright, so moving on, let us now apply Reynolds Transport theorem to the left hand side in order to take the material derivative into the integral. Before we do that, let us first write our Reynolds Transport theorem in a form that is more convenient for incompressible fluids, because in this derivation of the energy balance we are going to directly focus from the outset on incompressible fluids, simply because the derivation can be rather involved in the most general case, and it's something that you can find in any standard reference book. So therefore we are going to just focus on the case that will form the subject matter for this course. Alright, so let's look at the Reynolds Transport theorem once again. Transport theorem, right, but now for an incompressible fluid. Essentially we are going to try and find a slightly simplified form of this expression just for the ease of our derivation. Alright, so let's write it out in the general form in terms of some arbitrary quantity b, the way in which we derived it. Remember, this is equal to, from our earlier work, the partial derivative of b with time plus the divergence of b times the velocity u, velocity v, over the volume. But now this term can be expanded out as b times the divergence of the velocity plus v dotted with the gradient of the quantity b. And now we know the divergence of the velocity is 0 for an incompressible fluid. Yes? And then if we combine v dot gradient of b with dou b dou t, we see that this is simply the substantial or material derivative, but now inside the integral. So basically for an incompressible fluid, we have the simple result that the Reynolds Transport theorem allows us to directly take in the material derivative into the integral. So now applying the Reynolds Transport theorem in this simplified form, we can directly write down the left hand side terms as follows. So we have integral over the volume d dt plus d dt of v square by 2, v square by 2. Right, so I have written v dot v as v square times the density, of course, we shouldn't forget that. Oh, I believe I missed. Yeah. So sorry, I made a bit of a blooper here. So I initially said that E is the internal energy per unit volume. So then I need to add a mass term here. If E was the internal energy per unit mass, I did not need the density. But we'll work with the idea that E is the internal energy per unit volume, so that I can introduce some density here as well. Oh, I'm sorry, I forgot a density term here, which I've just added now. This is because E is the internal energy per unit mass, and so I need a mass per unit volume, and then only I can integrate it over the volume. So I missed out this density here, but no harm, no foul, I put it back in. Yes, yeah, so we've now got the left hand side of the equation by applying Reynolds Transport theorem. And now we can use a divergence theorem on these two surface integrals on the right hand side to get another volume integral. So we'll have rho g dot v plus, now here we have the divergence of t dot v, yes, minus the divergence of the heat flux vector. Yes, and there we have it. Note that this, as it should be, the energy equation is entirely a scalar equation, E being a scalar, V square being the scalar magnitude of the velocity, and everywhere we have vector dotted with a vector, the divergence of a vector, and again the divergence of tensor dotted with a vector, which is a vector which gives us a scalar. So everything looks consistent as it stands. So now we can use the fact, as we always do, that Vm is arbitrary, and that ultimately leads us to the point-wise differential equation for the total energy balance, which takes the form rho d T times the internal energy per unit mass plus the kinetic energy term, sorry, this is V, and this must be balanced by contributions from the work done by surface forces and the work done due to body forces and the input of heat due to the heat flux term. So yes, so let's just write here, this is work because of stresses. This is the work done by gravity, and this is simply the heat flux. Okay, so now this equation is the total energy balance. However, it's useful to bring it into another form which differentiates the contributions of work done by stresses and gravity to internal energy and kinetic energy separately. By that I mean, the way the equation is written now, it tells us how the mechanical work done by surface stresses and body forces go into the overall energy. In that sense, the internal energy and the kinetic energy is mixed. But often we might want to know how the work done on a fluid leads to its kinetic energy alone and its the increase of its temperature independently. And so for that, in order to decouple these effects, let's take the dot product, take the scalar product of Cauchy's equation with the velocity vector. Yes, so what will this give us? It gives us V dot, the substantial derivative of V with the density coming on the outside, is equal to V dotted with the divergence of the stress tensor plus V dotted with rho g. And you see that this term, if I take the V in, becomes d dt of V dot V, which is V square with a half times rho. So now if I subtract out the 2, you will notice that basically, let's mark this equation as 1, the total energy equation, 2 as the dot product of Cauchy equation with U. And now if I subtract out 1 from 2, you will see that this term, the kinetic energy term, will cancel out. The work done by gravity will also cancel out. We'll have the heat flux vector surviving, we'll have the internal energy rate of change surviving, and we'll have a difference between these two surface stress terms. So here we can use an identity. So we have the following identity, that a vector identity, which you can prove and which has been proved in standard books on vector analysis. So we just take it as a given here. So I'll give you a reference at the end where all of these identities have been proved, or it's shown how one can prove them using quite conveniently the Einstein notation. Right, so the difference between these two quantities can be shown to be the stress tensor times a double dot product with the symmetric part of the velocity gradient tensor. Let's call this identity 3. So basically, by subtracting 2 from 1 and using 3, we obtain an equation entirely for the rate of change of internal energy. So these are both tensors, of course. Minus the divergence of the heat flux vector. All right, so this is our internal energy equation. Which let me call 4. So what is the meaning of T double dot E? Well, it means that you take every component of the stress tensor, multiply it with the corresponding component of E, and then add up all that stuff together. So it gives you a scalar in the end. So now this is a general form, it's applicable to any fluid, but at this point we shall now specialize to the case of a Newtonian fluid, for which we know the constitutive equation for T, and for which we can apply the well-known constitutive equation of Fourier's heat law of heat conduction for Q. So we now look for a incompressible Newtonian fluid for such a fluid. Remember, the stress tensor is given by QE minus P times the identity, and then we can use Fourier's law of heat conduction, which says that the stress vector at any point, basically the heat flux at any given point, occurs in the negative direction of the gradient of the temperature theta with the constant K, which is the thermal conductivity. And now since we've introduced the temperature theta, so theta here is temperature, it will be nice to represent the internal energy per unit mass E also in terms of temperature, or the rate of change of that quantity in terms of temperature. And for an incompressible fluid, in which we neglect thermal expansion effects as well as pressure expansion, then we have that the rate of change of dE dt can be written as Cp times the rate of change of the temperature. So using all these ideas together, our total internal energy, our internal energy equation becomes the following. So we have rho Cp times the material derivative of the temperature is equal to the divergence of conductivity times the gradient of temperature. Now the negative signs are lost because of the constitutive equation where the thermal flux happens happens down a temperature gradient, and then the other term which comes from the surface stresses after applying the Newton's constitutive equation becomes simply 2 mu times E double dot E. Notice that only the viscous term makes a contribution here in the thermal energy equation, because the identity tensor when contracted with E simply gives you the divergence of velocity, and the divergence of velocity of course is 0 for an incompressible fluid. So for an incompressible fluid, pressure forces do not lead to any changes in the temperature equation. That is, we cannot convert, let's say, mechanical work into heat. So basically pressure forces cannot generate heat if the fluid is incompressible, although it can happen if it were compressible. On the other hand, viscous forces can generate heat, and that is what we call heat dissipation due to viscous forces, and that is this term here. So this is thermal energy dissipation or heat dissipation. We'll have more to say about this term in a moment. But okay, so this is the form that our temperature equation arising from the energy balance takes, which we can call phi. And you see now here I've left the conductivity inside the divergence, allowing it to be a function of space. If this were not a function of space, we could of course, if it were truly a constant, write it as k times the Laplacian of temperature. Yes, so then this term takes the form of thermal diffusion, and it becomes even clearer if I take rho Cp to the other side, in which case I can just write that the material derivative of temperature is equal to thermal diffusivity times the Laplacian of theta plus 2 times nu over Cp E double dotted with E. Sorry, I forgot my tensorial notation. There we have it, where alpha is the thermal diffusivity. So this is the form of the thermal equation, the temperature equation that we will be using in the rest of our course. And we will come back to it when we do the mass conservation equation to notice the analogy between thermal diffusion, mass diffusion, and viscous diffusion of momentum.